Greetings and salutations. The information presented in these videos was put together from many different sources. Rather than distract the viewer by citing them constantly, instead we will have separate videos where we examine the sources. The first one, beyond a doubt, is SICP, Structure and Interpretation of Computer Programs, by Harold Abelson and Gerald J. Sussman, with Julie Sussman. Also known as the Wizard Book. It is one of the most important classic textbooks in all of computer science. The foreword, by Alan Perlis, makes us immediately aware that this may not be the ordinary textbook. This book is dedicated, in respect and admiration, to the spirit that lives in the computer. Reading from Chapter 1, Building Abstractions with Procedures. We are about to study the idea of a computational process. Computational processes are abstract beings that inhabit computers. As they evolve, processes manipulate other abstract things called data. The evolution of a process is directed by a pattern of rules called a program. People create programs to direct processes. In effect, we conjure the spirits of the computer with our spells. A computational process is indeed much like a sorcerer's idea of a spirit. It cannot be seen, or touched. It is not composed of matter at all. However, it is very real. It can perform intellectual work. It can answer questions. It can affect the world by disbursing money at a bank, or by controlling a robot arm in a factory. The programs we use to conjure processes are like a sorcerer's spells. They are carefully composed from symbolic expressions, in arcane and esoteric programming languages, that prescribe the tasks we want our processes to perform. 1.1 The elements of programming. A powerful programming language is more than just a means for instructing a computer to perform tasks. The language also serves as a framework within which we organize our ideas about processes. Thus, when we describe a language, we should pay particular attention to the means that the language provides for combining simple ideas to form more complex ideas. Every powerful language has three mechanisms for accomplishing this. Primitive expressions, which represent the simplest entities the language is concerned with. Means of combination, by which compound elements are built from simpler ones. And means of abstraction, by which compound elements can be named and manipulated as units. In programming, we deal with two kinds of elements, procedures and data. Later we will discover that they are really not so distinct. Informally, data is stuff that we want to manipulate, and procedures are descriptions of the rules for manipulating the data. Thus, any powerful programming language should be able to describe primitive data and primitive procedures, and should have methods for combining and abstracting procedures and data. In this chapter we will deal only with simple numerical data, so that we can focus on the rules for building procedures. In later chapters we will see that these same rules allow us to build procedures to manipulate compound data as well. Section 1.1.1 Expressions. One easy way to get started at programming is to examine some typical interactions with an interpreter for the scheme dialect of Lisp. Imagine that you are sitting at a computer terminal. You type an expression, and the interpreter responds by displaying the result of its evaluating that expression. One kind of primitive expression you might type is a number. More precisely, the expression that you type consists of the numerals that represent the number in base 10. If you present Lisp with a number, 486, the interpreter will respond by printing 486. Expressions representing numbers may be combined with an expression representing a primitive procedure, such as addition or multiplication, to form a compound expression that represents the application of the procedure to those numbers. For example, if we add 137 and 349, we get 486. Subtract 334 from 1000, and we get 666. Multiply 5 and 99 is 495. 10 divided by 5 is 2. And if we add 10 and 2.7 we get 12.7. Expressions such as these, formed by delimiting a list of expressions within parentheses, in order to denote procedure application, are called combinations. The leftmost element in the list is called the operator, and the other elements are called operands. The value of a combination is obtained by applying the procedure specified by the operator to the arguments that are the values of the operands. The convention of placing the operator to the left of the operands is known as prefix notation, and it may be somewhat confusing at first, because it departs significantly from the customary mathematical convention. Prefix notation has several advantages, however. One of them is that it can accommodate procedures that may take an arbitrary number of arguments. As in the following examples, the addition of 21, 35, 12 and 7 is 75. Multiplication of 25, 4 and 12 is 1200. No ambiguity can arise, because the operator is always the leftmost element, and the entire combination is delimited by the parentheses. A second advantage of prefix notation is that it extends in a straightforward way to allow combinations to be nested. That is, to have combinations whose elements are themselves combinations. We can take 3 times 5 and 10 minus 6 and add them together to get 19. There is no limit, in principle, to the depth of such nesting, and to the overall complexity of the expressions that the Lisp interpreter can evaluate. It is we, humans, who get confused by still relatively simple expressions, such as the result of adding the result of multiplying 3, and the result of adding the result of multiplying 2 and 4, and the result of adding 3 and 5, and the result of adding 10 minus 7 and 6, which the interpreter would readily evaluate to be 57. We can help ourselves by writing such an expression in this form, following a formatting convention known as pretty printing, in which each long combination is written so that the operands are aligned vertically. The resulting indentations display clearly the structure of the expression. Even with complex expressions, the interpreter always operates in the same basic cycle. It reads an expression from the terminal, evaluates the expression, and prints the result. This mode of operation is often expressed by saying that the interpreter runs in a read-eval-print loop. Observe in particular that it is not necessary to explicitly instruct the interpreter to print the value of the expression. This brings us to section 1.1.2, naming and the environment, which we will cover in the next video. Until then, have a wonderful day.